We'll also be consolidating our standard documents. The documents will change and be organized so that developers can better find the information that they need. This includes things like Zigbee Pro specification, which talks about networking, and that's in the upper left-hand corner there. If you go to the right, Zigbee 3.0 base device behavior specification, and this describes how devices join and form a network. And if you go to the bottom left, it's Zigbee 3.0 application architecture. This is really implementation guidance for developers. And then last but certainly not least, in the bottom right-hand corner, the Zigbee 3.0 cluster library, and this defines the application level functionality. And this is really something that the Alliance has discovered several years ago is really a key component to the Internet of Things and bringing applications to consumers around the world. So with that brief introduction, I just want to thank everybody for participating today and our excellent speakers. I will now turn it over to a good friend and colleague, Phil Jameson, with the Philips Research Europe. So Phil, over to you.
Okay, thanks, Tobin. As Tobin says, I'm Phil Jameson. I'm from Research in Philips, and I'm going to talk a little bit about the base device behavior specification, which is something that which is quite new that we're developing, and it will support the interoperability requirements of Zigbee 3.0. So in the context of my talk today, I'm going to go through the network security models, what we've got there, the various commissioning mechanisms that we have, go through each of those in a little bit more detail. I'm going to touch on resetting the node and also security in centralized networks, and then I'll draw together some conclusions. So on the next slide. Okay, so the base device here it sits between the network layer of the Zigbee Pro stack and the manufacturer's application, and it supports the application support sublayer and the Zigbee device descriptions that we have. So it provides a consistent set of behaviors for nodes that connect to a Zigbee network. So they do that in a very consistent way. It supports a uniform application space, and one of the things that we've done in Zigbee 3.0 is remove the concept of profiles. So essentially, all the application space is now flat. It's no longer siloed like we had it before, and that provides a lot better interoperability between devices. We define a common set of mechanisms for commissioning. Again, I'll talk about those later on. And we have provided some enhancements to the security of the various networks that we support. So next slide, please. Okay, so these are the two security models that we currently provide. So the diagram on the left is probably what most people are familiar with here, and that's the centralized network that we've used in Zigbee for many years, and that network is started by a Zigbee coordinated device, but now we're saying that has also to be a trust center, also has to have that functionality to make the network as secure as we can make it. So essentially, nodes that want to join such a network, they join using MAC association, then they receive the network key, and they establish a unique trust center link key with that trust center, and I'll talk a little bit about that later on. But the diagram on the right is something that we've taken from our LightLink standard, and it's called distributed security network, and that differs from the centralized one in that there is no central node or no trust center that looks after the network. In order to do that, we have enabled routers to start networks which they couldn't do before. So they're able to start a distributed network, and devices that want to join such a network, they just go using the normal mechanisms of association. They receive the network key. Obviously, there's no trust center link key in this case, as there are no trust centers. But then everything is very similar to the centralized case. But the key important thing here, I think, is that nodes that wish to join a network, regardless of what that network type happens to be, it simply taps to the model of the network on which they're joined. So it's very flexible, and the nodes themselves don't need to know what type of network they're actually joining. So on the next slide, we'll get into some of the commissioning mechanisms. So on the right-hand side there, we've got a centralized network, and we have a node on the left which wishes to join that network. So this is network steering. So this is all about getting onto the network in the first place. So if you go to the next step, The first thing we do is we provide some sort of user interaction on the trust center. And this is to make things very, very simple for the consumer. And now what that does is it opens the network up for a short period of time, in this case 180 seconds. And then the next step is that we provide a similar sort of interaction on the node that wishes to join the network. And that performs a scan. That's a 15.4 scan. And then it associates with the open network that it finds. And on the next step, once the device has associated, it receives the network key, and in the next step, we exchange an initial trust center link key that all devices have with a unique trust center link key that has been generated by the trust center. And that's how hopefully we make that centralized network a bit more secure. So the next step is really after the timeout period, after 180 seconds in this particular case, then the network is closed, and that stops further devices joining the network. So that's steering. On the next slide, we have network formation. This is very similar in a way. Essentially, the node that wants to form a network, it does a channel scan, 15.4 channel scan. It selects a suitable channel and various other network parameters such as a PAN identifier. But the difference here is that if you're a coordinated device and you're doing this formation procedure, then you form a centralized network. And once you've done that, you initiate your trust center functionality, and that's how we get that security added benefit of the centralized networks. However, if you're a router device and you also do formation, you then form a distributed security network, and that's how we get to the two sorts of or two types of network. So on the next slide, we get into the application links, if you like, in this particular slide. So this is called what we call easy mode finding and binding. And this is for two devices that happen to be already on the network, but you need to find out what the application facilities are in each of the devices in order so that you can establish meaningful application links between the two devices. So this could be, for example, an initiator could be some sort of controller device, and the target might be, I know, a shade actuator or something to control your shades in your house. And then we do the same sort of thing that we did for network steering. So we have some, in the next step, we have some user interaction on the target device. And what that does is it causes the target to identify itself in whatever mechanism it could do. So it could be a LED that flashes, or if you've got a light source, you could flash the light, for example. And the next step, we do the same thing on the initiator. And what that does is it causes the initiator to send out an identify query request. What that does is it asks whoever receives this identify query request, if you're identifying yourself currently, then respond to it using an identify query response message. And that effectively allows the initiator to know the existence of the target, and then we can do further things. So on the next step, what the initiator then does, it requests the simple descriptor from the target. And the simple descriptor, which has been around in ZigBee for really since it started, contains information about the target. So it contains the clusters that particular target supports, and that's now passed back to the initiator. So on the next step, what the initiator does is it looks at the information it has from the target and the information it has from itself, looks to see whether there are any matches in the clusters that we have, and the next step, it generates some entries in the binding table, and then your application links are established, and more about that maybe in the next talk. So the next slide, please. So touchlink is another mechanism that we have, but this one is particular because it's for devices or target devices, shall we say, that don't have any application interface. So one example here could be the initiator might be some sort of remote control, and the target could be a light bulb. So you don't have any switches or any way of interacting with that device on the target. And touchlink works by proximity, so you have to physically move the devices in close proximity in order to make this work. And touchlink is not just about connecting a device to a network, it's also about establishing the application link. So it's like the steering part and the finding and binding part. So in the first step here, next step, you do some interaction on the initiator, and it sends out a scan request. And the targets that receive that scan request, they first of all look to see what the strength of that command, that message is, what RSSI value, in order to determine whether it is from a device that's in close proximity. So if the RSSI of that message is high enough, then it determines that it's a device that's close by, and then on the next step it responds with a scan response. And the scan response gives an indication of what facilities are on that target. In this case, it's just a device identifier. And on the next step, the initiator then asks the target either to start a network if the initiator is not already on a network, or it asks the target to join its network if it is already on the network. So that's the steering part. But then after that, the next step, what the initiator can then do, it can use the information that it got in the scan response, the device ID. In this particular case, it's device ID 2, and it can derive what clusters are supported on that device. In this case, 1, 3, and 4. It looks on the clusters that it itself supports and sees whether there are any matches, and indeed in this case there are some matches, and then it can create an entry in the binding table in exactly the same way as we had with finding and binding. So next slide, please. Okay, a little bit about reset, which is quite important here. Reset is again, it's very similar to what we have with commissioning, and we invoke it with some sort of user application stimulus, whatever that happens to be. And the base device spec allows you to do this in a number of different ways. So the identify cluster that we used in the finding and binding, it also has a facility to allow a device to reset. The TouchLink commissioning mechanism also has a mechanism to reset. And indeed, if you have something on the device itself, for example, a reset to factory new button or something like that, you can reset the node in that way. But the key thing here is that all of these mechanisms are all the same. They all result in setting the node to its factory settings, and that way it can be recommissioned if you did it by mistake or you want to move it to another network or something like that. So it's all consistent here. Next step, please. Next slide. Okay, a little bit about security in centralized networks. We have quite an exchange of messages here in order to establish the communication between the two. Here we've got a trust center on a centralized network and a new node that is about to join the network. And each device has an initial trust center link key, called it key A. And that might be a well-known key, or it might be derived from an out-of-band mechanism, such as an installation code. So the first thing that device will do on the next step is associate with a network in exactly the same way as I talked about in network steering, and that's an unsecured message because that's a 15.4 communication from the Mac. Next step, the trust center then sends the network key to the new node, and it encrypts that with the initial key that the node has. That's key number A. The next step, the new node itself requests a new key from the trust center. Again, it's using that initial key that it has, that it was pre-configured with before it started. And then the trust center sends a new key that it generates, they call it key B. It puts that inside a message, and then again it encrypts that with the initial link key that node had. And then on the next step, which is the final step of the communication here, we have a command exchange which allows us to verify that both devices understand what that new key happens to be, to avoid any missing commands and that sort of thing. So that's security in centralized networks, and hopefully that makes things a little bit more secure. So on the next slide, just to draw some conclusions here, networks can have either a centralized or a distributed security model, but nodes are able to join a network of any type, and they just adapt to it. There's no distinction between the two. There are common mechanisms, predefined mechanisms that we define and we standardize and make them mandatory in some cases for getting the device on the network and for establishing application links, and each mechanism they're all consistent with other mechanisms as well. And finally, on a centralized network, if a node happens to join a centralized network, then it replaces their initial link keys that they were pre-configured with a new link key that was generated by the trust center. Okay, on the next slide then, that's the end of my talk. If you have any questions, then as Ryan said at the start, use the chat function. But in the meantime, I will pass on to Arash.
Thanks, Phil. My name is Arash Honabacht. I'm Managing Director of Ubisys in Düsseldorf, Germany. And I will provide some insight into the application and cluster library. So let's start with a quick overview of device types that exist today in ZigBee. For one, we have the ZigBee green power device, which may be either unidirectional or bidirectional. And it consumes such few energy that you could power it using an energy harvesting module, or if it's equipped with batteries, then these would very likely outlive the lifetime of that device. Then next one is the ZigBee end device, which is typically also battery powered, but it is it draws considerably more power than a green power device, and it does not take part in the ZigBee mesh, but the ZigBee router instead, that's the backbone of the connected home or connected building or whatever application you have. It actually forms the mesh network for the end devices, for the green power devices, and for the applications that run on the routers themselves. And finally, the trust center, which Phil has talked about, it's essentially a more advanced router with some centralized management of security credentials and other centralized network management tasks. And from top to bottom, complexity increase. So next slide, please. So when we look at these ZigBee devices, and you have seen the Mac and PHY layer from 802.15.4, then above that the network layer defined by ZigBee Pro, and the application support layer. And on top of that, you have the manufacturer applications, which are on the endpoints 1 to 240 something. The other ones are reserved for future use. And you have the ZigBee device object, which is a kind of management endpoint. It's always on endpoint number 0. And all other endpoints built on the ZigBee cluster library. So next slide, please. So when we look at a single endpoint, and that's what device manufacturers typically will implement, then you can see that these endpoints are sources of command frames and destinations, and they are individually addressable, but you can also combine them into groups. And for example, if you have an actuator with 8 relays in one device, then you would create an endpoint for each of them, and then you could either switch 4 of them simultaneously or do that individually. Next slide, please. And so what clusters essentially are, they are interfaces for features or functional domains. So you could have clusters, for example, turn something on, turn something off. This would be a functional domain. And they are directional. So you have a server version of that cluster and a client version. And you could also say it's the inbound or outbound version of the cluster, And that essentially guarantees that when you do finding and binding, as Phil has explained, you get the mating devices to be bound together. So you have a plug and a socket and not two plugs or two sockets, to put it this way. And what's also important and makes this architecture very flexible and future-proof is that the clusters are the smallest interoperable unit in ZigBee. So if you have a certain client cluster that you have certified at the ZigBee test house, then you can be sure that you can control all ZigBee on-off server cluster devices. Next slide, please. Yeah, and as we saw, the cluster library, this is actually a framework which facilitates endpoint or device end device applications. So you can make use of attributes, commands, and these attributes can be set up to have a certain reporting, automatic feedback. You can use functions for discovery. You can be sure that, for example, if a command is not implemented in a previous version of a cluster, then you get appropriate status codes. So versioning is also part of this architecture. And in addition to this framework, it also contains a collection of standard clusters. So actually a kind of toolbox. You could compare it with Lego bricks that you can combine to create more complex applications. And yeah, as I said before, the client-server instances are interoperable out of the box. And examples for such clusters are on-off, to turn something on, turn something off. Level control could be used to set the intensity of a light, but it could also be used to set the speed of a motor or a pump, for example. Color control to control the colors of your smart bulbs, and so on. Next slide, please. So here is a simple example. It's a connected bulb. You have the management endpoint, the ZigBee device object at endpoint 0, and then you have the key endpoint for this device, connected bulb, will have a number of server clusters that are shown below, basic, identify, groups, and so on. And the most important ones obviously would be the on-off level control scenes cluster, and these allow you to create groups of devices and then have preset values for certain attributes combined in the scene. And so you could, for example, recall a scene when you go out the door, and you could combine these bulbs into a group, all ceiling bulbs, for example, and then press that button and say, okay, I'm leaving home, and then every bulb in that group and in that scene would turn off, while other critical devices like your refrigerator, for example, would continue to operate normally. And when you go to the next slide, then we see that the connected bulb has become a smart bulb by adding 2 more clusters. So we have a clever manufacturer who said, okay, connected bulb is cool, but I just want to add a motion sensor and an illuminance sensor, and then make that bulb not only connected but also smart. So it can autonomously decide when to turn on, at what intensity. For example, if it's dark and there is someone in the room, then okay, it will turn on. But if there is no one in that room, then there is probably no need for light. And that's one of the key differentiators for ZigBee, that this device, which is not known before, will still interoperate with the wall switch that has been there for 2 or 3 years and can send on-off cluster commands, because you have this kind of cluster included here, and the device can be controlled by the existing wall switch or by an existing gateway and smartphone app, which are able to communicate with these clusters, but did not know this certain or specific combination of clusters before. Next slide, please. So that's just a short overview of the device, ZigBee device object. You can use it for address resolution, to explore the mesh network, to add and remove bindings, look for certain clusters. You can do queries, for example, like what devices are color controllable devices in that particular network, or which device is an OTA server and hosts images that could be used to upgrade the firmware, and so on. Next slide. Yeah, so commands are actually some are comparable to methods in object-oriented programming languages. So you can use them to tell an endpoint to do something. So you can, in the easiest example, this could be a simple on-off command, but you can also include arguments. So you could say, okay, move the brightness to level 32 within 4 seconds, and then you will have some smooth transition on your light. And you can not only send it to one device, but you can send it to a group, then you have it multicast, or you can send it to all devices as a broadcast. Next slide. Yeah, attributes, obviously object-oriented approach, and you have the methods, the commands, and here you have the attributes. These hold their values in binary encoded format for different types. You can have arrays, structures, and it is possible to read, write attributes. You can do one-time programmable attributes. Attributes persist. You can control the access rights. They are reportable, and that's one amazing thing about attributes. You can just set up a notification, or you can subscribe to changes to that attribute. Say, okay, if it changed for a certain amount, then just send an attribute report, or send an attribute report every 10 minutes, for example. Next slide. So that's, again, the example with a wall switch, a dimmer switch. For example, the dimmer switch can send move to level commands to set the brightness, and the wall switch can just send only on and off commands, and both will be able to find the connected bulb, and both can send or can fulfill their function by sending the specific commands to that, which are specific to that cluster. And using the attribute reporting, you could easily have a gateway updated with status information, so that users have a feedback on their smartphones, whether a certain device is on, is off, at what level, and so on. And all this integrates very nicely and very smoothly with this concept. Next slide. Yeah, that's just the final example of when you would use the attributes or read and write attributes. You would do it for configuration, for example, on a level control server cluster. For example, the collected bulb, you can set an on level. So if someone presses the on or presses the button on the wall switch, then the device will turn on at the predefined level. That's one example. And the other example is a thermostat where you have occupied and unoccupied set points for the temperature. In this case, the thermostat could wake up and then query an occupancy sensor, which was previously bound to it, and see, okay, if someone's in the room, then use the lower the higher occupied set point for the temperature. Otherwise, save energy and drive the temperature down to, for example, 12 degrees or something. Yeah, thank you very much. Next slide. At this point, I would like to pass over to Ryan Maley, Director of Strategic Marketing at the Zigbee Alliance.
Thank you, Arash. I appreciate it. You've heard a lot today around the technical attributes of Zigbee 3.0, but I want to talk a little bit about the way that Zigbee 3.0 plays in the Internet of Things. Internet of Things is really a broad topic and the subject of much buzz in the industry, and means a lot of different things to a lot of different people. At the Zigbee Alliance, we think it's a relatively straightforward definition of what the IoT is, and that is really everyday objects communicating with each other and with people. And that enables a lot of really interesting things. And everyday objects, as you've heard our speakers discuss, must be very common objects. A great example is the light bulb. If you think about all the devices in your home, you may have a thermostat or two thermostats or one refrigerator, but you've probably got dozens of light bulbs. And there's a significant value to having these objects be connected and smart and work together. And really that's what the Internet of Things is, and that's what Zigbee 3.0 is designed to address. The wide variety of everyday objects in your home and your business that can connect and add value. And that's really one of the drivers behind Zigbee 3.0. As Tobin described, in the past perhaps we had divisions between certain devices, but over the years people have come to recognize that the more interesting applications happen because you have more different and diverse objects connected and communicating together. So what I want to talk a little bit about is what makes Zigbee appropriate for the IoT. You've heard some of the examples before, but I think that if you think about all the simple and smart objects in your home or in your business, you can see that to make IoT successful, you have to have certain things happening. For instance, your network must be very simple and easy to install and maintain. And as you've heard from Phil, we support a variety of ways to do that, but certainly the mesh networking of Zigbee and the self-organization makes it possible to create IoT networks quickly and easily. Of course, it must be very reliable. When you press that light switch, you want to make sure that light comes on, and I will talk a little bit about how the mesh helps that in a little bit. Lastly, something that's not often thought about is that the IoT must be very scalable. Tobin spoke about the numbers of billions of connected devices together. To have a scalable architecture that supports tens of thousands of nodes is really critical to IoT, and I think it's very important to recognize that technologies in IoT will need to grow to that size. There are some other attributes, but we can talk about those as we go, but what I'd really like to concentrate on is what we call the Zigbee difference, and there are a couple of things that make Zigbee different from other technologies that you may know. The first is something that's been discussed already, and that is that Zigbee is standardized at all layers. So it's not just enough to have the radios working together. You must obviously agree on what frequency is used and how transmission works. You also have to have the network at a common layer with understanding about how the addresses work and how the networks form. And as Arash has spoken about, you must actually have an understanding of what the application layer is. What is a light bulb? What is on and off? What is dim? You need standardization at all of these layers to have an interoperable product and assurance that product from different manufacturers will work together. And you have likely have a smartphone that has 3G or LTE on it, and that is interoperable certainly, but it is not just interoperable because of the 3G. It's actually interoperable because some of the applications on your phone, like your web browser, which uses application standards like HTML and HTTP to make sure that you can connect to any website in the world. So standardization at all those levels is critical and has been part of the Zigbee difference for quite some time. Second thing I'd like to talk about is the power of the mesh. ZigBee devices are different than other networking technologies you may be familiar with because devices will connect with every device near them. And what that means in our example here of a light switch talking to a light bulb is that even though you have a big network and this network is quite maybe geographically large, the switch may not be in radio range of the bulb, the target bulb. However, you can, one, use the power of the mesh to expand the geographic area of your network. You can use those intermediate nodes to pass messages back and forth so your initiator can reach your target appropriately. But the next, of course, important thing is that this provides some self-healing and robustness to the network so that if a preferred path may fail, a single device fails, you have alternative routes within your network to make sure that your network stays up and is reliable. And that's kind of an interesting thing about ZigBee compared to many technologies in that the more devices you have, the more reliable your network becomes. ZigBee devices are usually sleeping. They're not broadcasting when they don't need to. But when they do need to, they can wake up and they can deal with failures and make sure that your messages get through. Another part of the ZigBee difference is low power. ZigBee has been built from day one to be low power, and one of the biggest new features of ZigBee in the last few years is called green power, and it enables a device to not have an internal battery or not be externally powered. It can be powered simply with the energy that is harvested from a variety of means, the motion of pushing a switch or turning a handle, the differences in heat between one device or another, or even vibration. All of these energy harvesting technologies can be used with ZigBee devices to ensure that your ZigBee devices have the lowest possible power and are not reliant on batteries. For instance, if you think about those billions of connected devices, if all of them had batteries, we would spend our lives changing batteries. That's not really good for us or good for the environment. But with energy harvesting and the green power feature of ZigBee, you can ensure that your devices work very well without those types of implications. And this is just a small chart to show some of the examples of the differences in power usage compared to, in this case, Wi-Fi. ZigBee by itself is quite a low power device using, or a technology using 1/100,000th of the energy as compared to certain other technologies. And green power is even lower than that, so that you can have these energy harvesting devices that operate just on collecting energy from their environment, or may still be running on a battery but are in a difficult to access location and not easily accessible by people who can change batteries, and have very, very long life with minimal power use. Another part of the ZigBee difference is the scalability. We've spoken a little bit about that, but I just want to point out a couple of examples you can see on this slide. In particular, in the UK and Hampshire, there is a street lighting system with 90,000 connected street lights. You can see a little ZigBee node on the top of this traditional-looking street light. That enables all these devices to work together to understand their environment, to report on their status, and all in a single installation that can be controlled from a central location, and really improve the maintenance costs of these lights and make sure light is on for the citizens of Hampshire. Another example is the General Motors Spring Hill plant, which has 28,000 connected lights over 20 million square feet. And lighting updates are often done for energy efficiency purposes, and that was true in this case, although this installation doesn't use the most efficient lighting technology possible, like LEDs. It actually uses fluorescent lights that are connected, but that connected system and that very large system actually does things like sense occupancy and light levels and adjusts the energy, the usage of the lights based on that, and that particular system paid for itself in a year and a half based on energy savings alone. I want to spend just a couple of minutes before we take questions, and again, we've got some questions coming in as we're speaking here, but feel free to submit more as we're talking and we will try to get to them. Just a couple of IoT applications where Zigbee is in use, and some ideas for you in your business. Very popular area for Zigbee is the IoT in the smart home. And the smart home is kind of where the IoT touches our everyday life. Zigbee is really a great technology for that, used in a lot of environments, or excuse me, used in a lot of applications, and it really connects the widest range of devices that you might see in a home. You have a few examples here from security applications, connected lighting applications, energy efficiency, even audiovisual management in set-top boxes, televisions, remote controls, and all these wide variety of devices are with Zigbee 3.0 will help you connect into a single integrated network and allow you to create some very interesting applications, such as connecting your security system to your lights, so you can signal anyone anywhere in your home or those outside of your home if there is some sort of security condition. Another quick application on the business side is IoT in retail stores. This is an example from one of our member companies in the grocery business. And again, a wide variety of devices that can be connected using Zigbee. I'm going to talk about one little example, but you can see in here the idea is to improve the experience for the consumer, but also make the business as efficient as possible. And all while working in the background with these everyday devices that you might find in a grocery store. For instance, here's a small example of intelligent shopping carts. And what this diagram is showing actually is the activity and presence of carts at various locations in a store. And these shopping carts were tagged with a Zigbee tag, and they report their location periodically, and it allows you to analyze the data and demonstrate where those carts are, where they're likely to be. In this example, you can see some blank spots in here, which allowed the grocer to realize that some of the areas of the store aren't visited as often as they would like, and maybe aren't selling as many items as they would like. But it also demonstrates where everyone will eventually be at the checkout lane. So what this enables is that the grocer can actually predict when people will go into the checkout lane, and in terms of efficiency, be able to open up more lanes in response to shoppers in the store without adding more resource. And those lanes are only open when needed, reducing the wait time for the consumers, which is an important selling point. And also, this is all done just by tracking the everyday object, the shopping cart, rather than asking people to install an app or reporting otherwise on their location and using up their maybe using any privacy considerations from their smartphone. One other very quick example is another IoT in kind of a smart city application. This is for a parking lot and city parking, and you might be able to ask, well, why is it important that we know whether a parking space is open or closed, in use or not? And the answer is that it's actually quite efficient. I'm sure everyone has experienced driving around and being frustrated by not being able to find a parking space. But by being able to know these things and report them up to people, having these empty spaces communicate to people, you can also save energy because you are not driving around looking for parking space. So this is actually an important problem in larger cities, and is actually being recognized as a source of pollution, not just frustration for drivers. And again, Zigbee is a technology that can connect these kind of devices and deliver the benefits of IoT to consumers and businesses alike. So that's the end of my part of the presentation, and we do have some questions from various folks that have been coming in, and we will try to address a few of them now, and we can follow up later to those who've registered with answers to the other questions in writing. So let me go ahead and maybe Phil Jameson, I'm going to ask both Phil and Arash maybe, if you could comment on compatibility with Zigbee 3.0 and existing Zigbee standards. In particular, if I'm building a device today, will I be able to work with Zigbee 3.0 when it is released?
Okay, so I'll go first. Yeah, that's a big issue here, and that's something that we recognized very early on in the development of this process. So right at the start, when we looked at our requirements, one of the key things that we had to make sure we got right is, as you say, backwards compatibility with our existing deployed devices that are right there now in the field. So really, we took that on board, and we did some exercises to look at the profiles that we have and how we could improve them, bring them together, while bearing in mind that they have to work with 3.0 and what was out there now. So backwards compatibility, we definitely thought about and taken into account. Forwards compatibility, we have mechanisms in place to define what rules we use to develop new devices out there. Base device, of course, is something that we're going to use moving forward, and that provides the consistent mechanisms that we use to operate on the Zigbee network. So we also have that forwards compatibility in place as well. So really, anything developed from now on will certainly follow these requirements. I think we're geared up for that already, and also the things that are out there now in previous versions of Zigbee will also be compatible.
Yeah, I would just add that we also have, with the next release of the cluster library, we will have all the clusters that have been developed under the previous profiles will be available in one cluster library in one place, so device makers can make use of all of them. And when they build their device today, they can rely on the stack vendors to have the framework ready for Zigbee 3.0 when the certification program is ready as well.
Thank you. Can you talk a little bit about the encryption? I think it was covered fairly well by Phil, but in particular, what is sent in the clear? If you could just recap that, and how the keys are worked for, whether there are unique keys for the TCLK, etc. Phil?
Yeah, do you want to go back to one of my previous slides, or are you? Shall I just, if you go back to the one right at the end of my talk, essentially when you're associated to the network, that's in the clear. That's 15.4. So if you go right back to the start of that that sequence, so because that step there, the legend that we have on the right-hand side, it illustrates what security we are using on the messages. So the association is in the clear. The next step, which is the transferring the network key, we do use the initial trust center link key. We have a well-known key that we use. And we've used that for some time, and that's why we added this ability to update that key with a unique key that's been generated by the trust center once you're on board. So the bulk of the communications once you're joined is using the initial link key, right up to the point where you exchange that with the newly generated key that only the new node and the trust center will know. And then once that's successfully exchanged, and again you're using the initial link key to encrypt this, then you have the new key that you can use moving forward. So also we have this ability for installation codes as well. Every device will support installation codes, and that's a number that you can use on both devices, on the new node and on the trust center itself, and use that unique number to derive a unique link key. And you put that on the node, you put that on the trust center before you decide to join the network, some out-of-band mechanism, and then you can use that for your initial link key as well. But again, even though you've done that, you've taken that step to make that bit a little bit more secure. We still have this exchange where you receive a new touch center link key. So that replaces any initial link key, whether it's a well-known or whether it's installation code derived. It will replace that with a more secure key.
Thanks, Phil. Arash, I have a question about binding tables and where and how they are stored, and maybe you could comment on that and how that affects the hardware requirements for those end devices that have to store those tables.
Yeah, so the binding table is for the operational clusters, it is stored at the source. So where you send, for example, the on, off, or level control or whatever command, it must know where to send it. So obviously the binding table is stored in flash memory on that device, and it can address either a unique device identified by its hardware address and an endpoint number, or it can address a group, which is just a short address, and it can also address multiple targets per cluster and source endpoint. So you can send, for example, with one press, you can send to 5 different targets, for example. And for the bindings, for the reports, for the attribute reports, you would also use binding table entries. So this is on the server side, for example, on the light bulb, the on-off cluster. You would have binding entries for example, for the gateway, which shows your UI. And yeah, the memory requirements are, I think, perhaps 16 bytes or 8 bytes per entry, so that is not very much.
Okay. Thanks. We had a couple of questions about energy harvesting, and maybe I will take the opportunity to answer that. In particular, what kind of harvesting is used with Zigbee? And Zigbee is actually a communication standard and doesn't actually define the energy harvesting technology itself. We've seen many different applications of energy harvesting in green power-based devices, from piezoelectric, from various manufacturers, to solar, to even Peltier kind of heat differential. And the point of that is that Zigbee is designed to lower the energy requirements for communication. It does not actually define the energy harvesting technology. So whatever your energy harvesting technology of choice is or preference, or might be particularly suited for the application, should be able to work with the green power feature of Zigbee. And it should, if it's because we support this very low energy usage, most energy harvesting applications or technologies will work just fine. So as you're creating a green power device, you have a choice of that as well. We've got just a couple more minutes here. In fact, 2 or 3 minutes. I want to be respectful of everyone's time. I can ask one or more question. Phil Jameson, I was wondering if you could talk, you discussed the distributed and centralized security models. I'm wondering if you had any comments about when a particular model would be more appropriate for use. What type of application, for instance?
Yeah, sure. I mean, the distributed case is really for maybe more in the home sort of application, I would think, because it's very easy to set up, particularly in a lighting environment where you don't necessarily have that central device that you can use to distribute the keys. Of course, if you do have that, then you have a gateway or something like that. Then that is something that you could also use in a more complicated or more advanced home automation system, or indeed moving out of the sort of consumer space, more in the commercial space, or even the energy space. So it does, of course, depend on the type of application, but the distributed case, the key thing here is that it's very simple to set up, and you don't have to go through this exchange with a trust center. But if your application requires that, then your best bet is to use a trust center model.
Okay, thank you. I actually have 1 minute before the top of the hour. I know there are a lot of questions that we haven't been able to get to. I appreciate everyone's attendance, and just to tell you a little bit about what we'll be doing, as I said, we will actually be sending a link to everyone who's registered on the program, and we will actually include some answers to those questions that we weren't able to address that were submitted. So look for that over the next few days, and we will certainly try to address your questions. In the meantime, if you have any questions, you can spend a little more time on zigbee.org and take a look around. And if you would like to participate in the standards development process itself for Zigbee 3.0, we would love to have you consider joining the Zigbee Alliance today. Just to close off again, thank you very much for your attendance. We appreciate that very much, and have a great day, and we'll be following up with you over the coming days. Thank you.